Thank you. So, yeah, I'm Dan Smith, head of data engineering at 6.6. We're a London-based consultancy. So I guess the first question is, well, what does government scale mean, right? So people talk about web scale to mean things that are really big, right? Whereas kind of government scale, what I mean there is there's a lot of variety as well as volume, right? So there's a lot of data that looks different to each other, connects in different ways. So one of the ways to kind of get an insight into this is to look at this linked open data cloud. This is open, released public data. And all the colors here are different kind of areas, right? So you've got like government, geography, linguistics, life sciences. That's that big blob on the left there. And these are kind of connected and put on this map basically based on how close they are. So if we just isolate government stuff, you can see it's kind of across the whole piece, right? So it's connected to lots and lots of different areas, right? Of course, this is just the open bit of data, right? But the UK actually is tied second globally for the amount of open data that we release. So through sites like data.gov.uk, NHS Digital, UK Data Archive, there's somewhere like about 25,000 different data sets, and that's, again, just the bit that's open, right? So when you open data, it's not just fit for purpose, it needs to be fit for repurpose, right? And that means it's going to be used for a variety of purposes that are kind of unknown to the people making it open, right? That's kind of the point in some ways. So that makes it kind of tricky, right? And that basically means that like data quality at government scale is like all the edge cases in the private sector all brought together at once. There's a really good document called the Government Data Quality Framework, but this is based on kind of the practices and principles from the Dharma framework. So one of the things we looked at was, well, is this practical to implement in real work, right? So these are the kind of 6 Dharma principles. And what you kind of get is that when you do work like this, you're always part of a data supply chain, right? You're not the person gathering the data, you're getting data from lots of places, right? And what that means is you can do automatic checking of completeness, consistency, uniqueness, and validity, but it's kind of impractical usually to know if the data you've got is timely or accurate to real life, right? So, and this is because of these data supply chains, right? So within a data lifecycle, you collect some data, you do some processing, and then you exploit it or you share it. And then those normally feed into other data lifecycles, and you end up with this thing where the complexity gets multiplied up and up and up as you go down, down and across the chain, right? So there's basically these like compounded, cascading chains of data. So to do this, to kind of deal with that at scale, one of the kind of ways to work is to say, we're not going to just correct data, we're not just going to do data cleaning. Instead, we're going to kind of enhance the raw data that we get, and then basically add on some data quality features to it. So that basically means not just saying, we think this is wrong, we're going to fix it, and then we're going to give it to you, but to say, here's some data, and we've enhanced it and added markers that say, according to this rule, this bit of data looks wrong. Or according to this rule, the correct version should be this. And then letting the consumers decide if they trust that or not. But also lets them look at the raw data as well. So they can say, well, we're getting some weird results based on this source. Let's see what the real thing was before they suggested this transformation, right? And because in like the cloud and everything, storage is basically really cheap now, we can just do this at scale now, right? So one of the things that kind of this whole way of working kind of needs is to basically be able to support things without knowing the schema ahead of time, right? And indeed, in a lot of areas, the schema evolves. So if we look at historic data, so say we've got like an event bus or a message queue or something where data's basically evolved over time, we want to do data assurance and data quality over the whole history of that data, which means that things that are in an old schema are still basically in our remit to look at, right? So we're looking at things as they've evolved. So you'll see things like this, where there may be the first version of a schema maybe looks quite simple, it only does a few things, and then over time, things get refactored and changed, include more things, and get more complicated, right? So this means that when we're kind of loading data using our process, we're basically not saying like, let's just do like JSON to class deserialization, right? We're saying, well, we can't really do that because if we did that, we'd need to basically have like an infinite number of unmanageable classes and then have lots of logic everywhere. So instead of that, we basically have to say, well, we don't know what the data is going to look like. We need to support that, right? So we need to basically assume that the input data is of poor quality and it doesn't conform to schemas, right? And that way, if we work in that way, from the get-go, we're basically saying that hopefully will reduce the amount of undefined behavior that we kind of have to deal with. So the way we do that is to basically create our own kind of simplified wrapper types for this data. So I'll show you this. And to basically kind of reduce the amount of kind of different types we deal with once everything hits our stuff, right? And once we do that, it basically means we've kind of, most of our code always has like compile time, type safety, and if we write enough unit tests, then usually if it compiles, it will run over all the data no matter what it looks like, right? Whereas if we were using this in a language that wasn't as strictly typed, then you kind of wouldn't get that. And this really helps with like an agile development, right? So what this kind of looks like in practice is, I've got some data, it's got a bunch of any's in it, what am I going to do? And then basically taking that and then saying, right, let's have our own set of things called records and strings and longs and doubles and things. And then remove all of this other stuff, right? So that we basically cover everything in one place. And this kind of depends on what your JSON or whatever parsing library does. So in the case of some of the stuff I've been doing, in one of the cases I used DSL JSON. It seemed to be really reliable. It benchmarked really, really well for what we were doing in Spark. But yeah, it's like, it gives you a bunch of weird classes that basically, you don't want to have to like deal with all the cases. So instead, throw loads of data at it, see what classes come out, and then just capture them at start, right? So then what we ended up doing was saying, right, there's this first place where there's a bunch of undefined data, like maybe it's got nulls and other weird stuff that we don't really want to do in Scala, right? And then map it to this, where you've kind of got this really kind of simplified, kind of constrained model of what's allowed. And this is all basically just to reduce the type scope of the profiler, right? So that all the inputs and actually outputs just these, right? So when we talk about data quality, we also talk about kind of assertion rules, right? We could talk about these in different types. So a type A rule is basically one that works on a single field. So you basically take a single field, whatever that value is, and run a rule over it. And that means you can do things like data dictionary conformance. So the rule is this should be in this data, this should be in this postcode, or this should be in this piece of reference data, or it should look like this, right? Or you can specify what the encoding or the structure needs to be, right? It needs to look like a date, it needs to look like time, right? And also with the type A rule, because you're just working on a single field, you can take steps to improve your data collection. You can say there's a very simple validation rule. If we hook that into to where we collected the data in the first place, then we can basically validate that before the data's basically bad later, right? A type B rule is one that works at the level of a whole record. So this allows you to basically corroborate data points across that record. So for example, you might say that someone's birth date should be before their like date of death or that kind of thing, right? So like within a record, things need to be logically consistent. And similarly, like kind of, and then you're kind of limited to logic that happens outside of that record. But in the case of type A and B, parallel processing of these rules is very efficient because you can just take a very small bit of data and just do that without having to look at anything else. Whereas a type C rule is something that happens more at like process level. It's basically across records. So it's kind of rules that depend on the kind of business logic you're dealing with, basically. But these are like cross-cutting checks that are relevant to whatever decisions are being made down the line by the business, essentially. And there's like a type D rule as well, which is basically anomaly detection. And this is where you can basically get some data scientists, use all this kind of big data stuff we're working with, and basically use machine learning to do anomaly detection, to basically say, everything looks fine to me, but let's see what like AutoML and those type of things like think about it, and then pick things out that you can then use to build up type A, B, and C rules, right? And in fact, there's been a lot of work on kind of ML for DQ, basically. But I think it's one of those areas where a lot of that will just grow in the next few years, basically. So one of the techniques we use is something called profile masks. And this is where you can basically use character substitution to fold strings down to their patterns, right? So if I've got a data set with 1 million names in it or 1 million postcodes, it's quite difficult to kind of jump in there and figure out, well, how am I going to look at those and work out what looks right and wrong? Whereas with with profile masking, you can basically say, okay, so in the case of Joe Bloggs, if I replace all uppercase characters with an uppercase A and all lowercase characters with a lowercase a, and replace basically all numbers with a 9, then you kind of get like a pattern of what the data looks like. So in the case of Joe Bloggs, it's like a name, and it just looks like right? And then a date looks like 99-9999. And if you look at these postcodes, these are all valid postcodes, but there's only 3 different masks between them, right? So the first one is, I guess it'll make more sense, I guess, if you're sort of from here, right? But the first one is like a central London postcode. Most people don't have a postcode that looks like that, whereas the 2 in the middle and the last one are basically what most people postcodes look like, right? It's like AA99AA. So that kind of helps, but there's still a few different types. And if you carry this on, do what we call a low-grain data profile. That's where you take the high grain and you basically fold in all of the repeated characters. So a name becomes AA space AA. And that pattern basically captures quite a lot of names, right? The cases that it doesn't is people have hyphenation, if they have lots of middle names, and if you go outside of basically like our culture and you go around the world, lots of people do have lots of middle names and hyphenation, that kind of thing. And if you look at like dates, it's kind of the same thing, right? Dates, you kind of want them to be like 999-999, and if they're not, there's definitely something wrong. So you basically, this gives you a quick way of seeing all the stuff that doesn't conform to just a pattern. And the thing that's good about this is I've known nothing about this data before I ran this. I just say, do this, and then it's done this for everything. So I can run this on any field because I didn't know the schema of the JSON before I started, and I can just run this technique on every single value, and I didn't know those values either. So now I'm suddenly seeing, oh, wait a minute, these are the patterns of everything, right? So if I kind of just jump into postcodes a bit more, if you aggregate up the counts of all the patterns, you kind of see a distribution like this, right? Where the top 2 are basically the main 2 patterns of postcodes. And you can see their counts are really high, right? So there's like 500,000 that look like that, and then kind of 47,000 like that. The next most common is like nulls. And then there's this like kind of almost cliff point, right? Where this long tail of stuff that's probably wrong starts. And this basically allows you to start to see things that look weird. And then as the kind of like, I guess like cardinality, like occurrence gets smaller, you start to just see like really weird bonkers stuff at the bottom, like Shropshire, which is, it's a county, it's not a postcode, right? So what this has done is I've taken basically all the postcodes in like a sample of a database, and I'm able to show you on a single slide all the patterns in that entire, I guess like 600,000 postcodes. And they're all just there. Like a human can look at this right now and tell you what's wrong, what's not, and it's really scalable, right? And if we move on to talking about rules, so not just patterns, but rules, you can kind of use the same technique to basically say, right, I can create a rule. It's like a profile mask, but instead of outputting a pattern, it's outputting a Boolean true or false. So I'm basically saying, okay, I think it might be useful to know if a string has only alpha characters or not, or if only numeric characters. And you can see for these different values whether they're true or false or not, right? But you can get quite specific here, right? So I can say, I want to know if it has no white space, because you might say that a first name or like a family name shouldn't have white space. And then I want to see what the values are that don't conform to that. And from that, you can quickly see if that's a good test or not, right? Like, so in the case of like names, probably not, right? Lots of people have first names and last names have white space and hyphens and that kind of thing. But for data where you don't know the domain, you just don't know, right? So it's like a good test to kind of get in there and ask questions. And then you can start to have conversations with the business and with the domain experts about what's going on. And then also things with like dates. You can say, I want this to be ISO 8601 compliant, right? That's a really good test because that's probably exactly what you want anyway, right? Or just really specific things like, is this today? Is this column today, right? It sounds like a weird one, but like you definitely end up in like creating this in production because there's lots of things where you say, if it's today, that's a problem, or if it's not today, it's a problem, depending on what the data is, right? So one of the things you kind of, I sort of mentioned this before a bit, but basically like type A rules work on field level, and then as the types go up, you end up working at kind of record and data set level, and that affects the parallelization of it, right? But But as some of the speakers before were talking about Spark, Spark is very efficient at scaling this kind of thing, right? Because there's a lot of parallelizability in it. So one of the things we did to kind of simplify this and let it scale more is to basically reduce the output of this to basically a single feature. So the assertion rules and profile mask output in the same way, right? And what that allows us to do is to analyze them in the same way once we've got all the results. And to do this, we basically got like a flat kind of output, which looks like this. So our output looks like a row which just has the record ID of the original record, the JSON path of the value, what the original value was, the name of the function we ran on it, so if it was a high grain or low grain, or if it was one of the rules, and then the value of that. And then we basically have, depending on the application, a number of kind of dimensions of the data. So it might be that you know some of them have different source systems or different owners or whatever, right? But other things that you know would be useful when you're like slicing and dicing the actual output when you're analyzing it, right? So what you end up with is like loads and loads and loads of these, where you basically see original values, lots of functions run over them, and then those outputs from profile masks and assertion rules. And then when you aggregate these up, you get what we saw before with the postcodes and the cliffs, and you can quickly see for a given path what a sample of that looks like and what the counts are and where data starts to look wrong, right? So another thing that's useful with this is because it's so simple and flat and tabular, it's directly compatible with data frames in pandas. So a lot of data scientists will use notebooks and pandas and Python, and the way all this stuff works basically is just you just store it all as Parquet files, and then it's directly loadable using pandas or Dask or whatever in Python, which speeds up everything, right? So the way we do this is basically the profiling bit is a bit like the map phase in Spark or in EMR, right? So that's really highly parallelizable, and then the reduce operation, again, is really efficient to basically just do counting, because that's what Spark does best, right, is counting from lots of nodes. And then I guess the top tip is if you are doing this in AWS, you want to really minimize what you write, because S3 writing seems to be the biggest bottleneck. But also, if you're writing billions of things out, you've got to kind of work out how you're going to read that stuff anyway. So most of the time, we just output metrics, things that humans can look at, right? One thing that's important is being able to kind of sign off rules with business people, right? To be able to say, okay, we've applied these rules, so we think the data looks good. And while that makes sense to me, it needs to make sense to people that own that area and are responsible for it. So one of the things we've done in our design is to basically try and have a really unambiguous implementation of rules. So one of those things is to basically say, okay, a rule has a name, and that name completely defines the logic, right? So the name might be max length 3. Behind the scenes, that's implemented as a parameterized version of string max length, right? And what that basically says is, okay, so I can see the parameters, so I know that what a null will do, and I know what the length is, and that's kind of all you need, right? Because then you can kind of easily debug that. So you know, no matter what the string is, if it's a null, if it's a string, this is the output, right? And the idea here is that you can get this signed off, right? And if people ask questions of it, this is all they need, right? And there's a neat trick here as well, right? Which is that in data quality and assurance, there's two things, right? There's all the data we've made in the past, and there's all the data we're going to make in the future. So it's one thing to look at the past and fix it, but you also want to make sure that those rules that you're creating are enforced in the future as well. And the cool thing about using Scala for this is that we can then use Scala.js to basically take our Scala rules that are nice and neatly unambiguously defined and then put them in the UI. So with basically that bit of code, I can basically export all of my rules to JavaScript, and then this is me just like testing the prototype in the console, and it works. So that means I've kind of got backwards fixing and future validation all with one piece of sign-offable logic, right? And by aggregating all those rules, by saying, we're basically doing two things, right? Top down, so like enterprise data architecture governance to determine what the rules should have been in their design. And then bottom up evaluation of issues found in production. So whenever there's been problems that haven't been covered by the EDA work, but things that have been problems in the past, I can take all of those, make rules for all of them, And if all those rules pass, then you can say those records are assured. And then you can say how much assurance, what percentage of records are assured, basically, right? One thing that's really helpful here is to have human readable output. So this is some output from our code. Our code's called DQ6. And this is basically a single field in Companies House. This is like the UK Register of Companies. What you can basically see is, firstly, the compliance to rules. So there's kind of 6 rules here. There's 4 of them are about years and dates. Company names aren't dates, so there's 0%. That's kind of good, right? And then the others, the rule of the rules says the company number shouldn't be blank. So that's actually 100%. And then there's another one which says only alphanumeric characters are permitted in the company number. And that's actually not 100%. So there's some issue, but only with 15, which is not bad, right? And then the other thing it shows you is basically a histogram of the profile mask patterns, high grain and low grain. And then the top and bottom 10. So the top 10 are basically the ones that are probably good, and you can see that where the cliff happens there. So the first one is all numbers, the second one is all numbers, but the example starts with SC. This is actually Scottish companies, that's completely valid. Then after that, there's a few more that look a bit like something's going on, and then after that, all bad. And then, as I said before, all the bottom ones, just like bonkers weird stuff. In this case, it looks like bits of addresses, bits of company names. They're definitely not company numbers, but straight away, I know these are clear errors, and we can write rules to fix those, right? So I guess the final thing is to say, if we go beyond the technical, you go through this process, you've done a lot of data analysis, business analysis, you've produced the data rules, you're going to remediate your existing data, validate your future data collection, and the last thing to do is like calculate the savings, like what's been the bottom line of all this work? Has it saved money? What does it cost, right? And use that to increase future investment. And there's loads of work on this, right? So I would say, if you're in this space, definitely look at things like Tony O'Brien's paper, which is, it's got a great name, it's Accounting for Data Quality in Enterprise Systems. And it gives you a whole framework of how to cost out the problems that bad data causes, and also the costs of fixing that down the line if you don't fix it early. And if you do this, then you'll be able to justify all this work, and it makes the business better, right? So yeah, the final thing to say is, if you want to work on large-scale, complex problems, please apply for a job with us. We are hiring in all these areas. These are the kind of clients we're working with. And if you want to send me an email or add me on LinkedIn to get in touch, please do. Thank you very much.